Hello, hello, hello. We are in the process of discussing applications of the integral, and we're on the topic of work. This is a part 4 of section 6.4 from James Stewart's Calculus Early Transcendentals book, and we are discussing work. And remember that work is equal to force times distance. Good. And today's topic involves pumping liquids from containers. I want to emphasize the importance here of following the problem-solving procedure. And what is the problem-solving procedure? Usually I say, read the problem. Okay, read it again. Figure out what it is that you need to find. Next, draw a picture. Label the picture. If you have unknown quantities, put in variables. Put in as many facts as you know into the picture. Go back to the problem, find the question that they're asking you to find. Go back to the picture and the question and try to establish a relationship, and that relationship is formulating an equation. And then once you have that equation, classify it, put it together, solve. And in this case, since we're dealing with applications of integration, we're probably looking at something with our work formula here. Work is force times distance. Remember, when force is constant and distance is constant, then we can just go ahead and use the formula and calculate, take the values that we have and plug them in. But if either force or distance or both are variable, that's when we need to put calculus into motion. Because remember, calculus tends to divide the region that we have, or divide the tank or whatever region that we have in the plane into slices, delta x slices or delta y slices, and we tend to approximate the area or the volume or whatever we need to find on that slice. And we assume that along that delta x or delta y slice, since it's very small, that anything that varies is actually constant along that slice. And then we go ahead and add up all of our slices and let the number of slices go to infinity, and that's what brings an integral into play. And our limits of integration are always going to be the range of our slices. Good. So I'm going to draw a picture here. Before us, we've got a problem. We've got a cylindrical barrel that's half full of oil lying upright. The barrel is 10 meters long with each circular end of radius 5 meters, and it's asking how much work is required to empty all the oil through an outlet at the top of the tank. And it says use the density of oil, densities of liquid. Remember, liquid occupies 3-dimensional space, and your density is usually going to be measured in either kilograms per meters cubed, and that is a per volume, or your density is going to be measured in pounds per cubic foot. Those are tend to be the standard units of measurement for the density of liquid. Okay, so here we've got oil. I'm going to draw my picture. I've got a cylindrical barrel that's lying upright. I'm going to fill it halfway with oil. We'll call our oil gray. I don't really want to make it black because I want you to see the shape. And we're going to be pumping out over the top. And the reason why we need to use calculus here is that we're going to divide our oil into slices, but what's varying is that with each slice, the slice is going to have, because the cylinder is uniform, each slice is going to have a uniform force or constant force, but the distance that each slice has to travel is going to be variable. And when we have variable distance, we need to use calculus or any of the variations with our force times distance. All right. I tend to think that wherever you need to pump it out over should be the 0. So I'm going to put 0. I'm going to draw some axes here, and I'm going to put my 0 at the top of the tank. And I'm just going to label that axis X. It's okay if you want to label it Y. If you want to use vertical axes as always the Y axis, that's fine. You're just going to be developing an integral in Y, and that's fine. We do know that the height of our barrel is 10 meters long. So I know I'm going to go from 0 to 10 here, and I know that it is half full of oil, so I know that this position here is 5. And also I do know that the radius of my tank is going to also be 5 meters. Good. All right, now I'm going to, again, we're going to divide our oil into delta X slices, and I'm just going to draw a random X slice, right? There's my slice of oil here, and since I'm slicing the x-axis, the height of that is delta X. And if I were to pull out that slice would look like this. Right, and we'd have delta X, and it would be 5 meters. Good, and that is my slice of oil. Okay, and I think that that is helpful. And so I want to take back a look at the density of oil, and we've got work to find. What is work? Work is force times distance. What are the units of measurement in force if I'm dealing with measurements here that are in meters? Then I'm dealing with standard international units of measurement. So the unit of force is the Newton. And remember that force is equal to mass times acceleration, and our acceleration here is our gravity constant. And our gravity constant in meters per second squared on Earth is going to be 9.8 meters per second squared. So let's not forget that. But I'm going to go ahead and set up my integral here. So I'm going to start with, what is my delta mass of my slice? All right, this is mass of the slice is our delta mass. Okay, just for notation purposes. I need kilograms because mass is kilograms. And so I'm going to use my density here. And my density is 881 kilograms per meters cubed. And I actually want to multiply by the delta volume, because that's going to be in meters cubed, right? Because then if I wanted to cancel my meters cubed, I would end up with 881 times the delta volume, and I'd have kilograms, and that's going to be my delta mass. So what is my delta volume? We've got, this is the slice of my oil, and remember that volume of uniform shapes, which is, this is a uniform shape, is area of the base times the height. So I see here that my delta volume is going to be pi r squared times delta x, because delta x is the height of that slice, and the radius is 5. So I have 25 pi delta x. Good. So my delta mass here is going to be 881 times pi r squared times pi 25 pi delta x. Good. All right, so that's delta mass. What is delta force? What is the force on that slice? So the delta force is going to be delta mass times acceleration, and the acceleration is due to gravity, and that's going to be times 9.8 meters per second squared. And so I'm going to get 881 times 9.8 times 25 pi delta x. That's my delta force. Good. What is my delta work? My delta work is going to be the force on that slice times the distance traveled. by that slice, right? And the distance traveled by that slice, remember, we want to use, that's why we want to put 0 at the top of the tank. What is going to be the distance to my slice? The distance to my slice is going to be x, right? Because an arbitrary distance out from 0 along an axis is going to be just that variable, whatever you labeled that axis. If you labeled that axis y, 0 to your slice is going to be y. Good. So now I can write that my delta work is going to be delta force times distance, and that's going to be 881 times 9.8 times 25 pi delta x, and my distance down is going to be x. Good. Now, what are the range of my slices? The range of my slices start at 5 and they go to 10, right? So this is going to be an integral from 5 to 10. So my total work is going to be the integral of my delta work. The range of my slices is 5 to 10. And I'm going to get, and I can put my constants on the outside. It's going to be 881 times 9.8 times 25 pi. And my integral is going to go from 5 to 10 of x dx. Good. And when I make that calculation, you can do it on your own. It's a really simple integral to calculate x squared divided by 2. And then we do the fundamental theorem of calculus, and our units of measurement for work is going to be the Newton meter, because we have the kilograms and the meters, so that's going to be the Newton meter, or you can call it the joule. Good. And so that's how you set up pumping liquid. So let's take a look at another example where maybe the force and the distance might be variable. And so here we go with that. All right, so here it says a tank in the shape of an inverted cone is full of water. If the height of the tank is 10 feet and the radius of the top is 4 feet, how much work is done emptying the tank through a spout that is 2 feet above the ground? Use the fact that the density of water is 62.5 pounds per cubic foot and round your answer to the nearest foot pound. Okay, so I guess the implication here, because I see through a tank of 2 feet above the ground, the implication here is that the tank is below ground where the top is at ground level, right? And the spout is 2 feet above. Okay, so again, problem solving procedure. Let's draw a picture of the cone. So I'm going to draw a cone. Good. I'm going to draw my facts. I do know that my facts in here, I know that this is 4 feet. I know that the height of my cone is going to be 10 feet. Okay, I know that there's going to be a spout that is going to be 2 feet, right? Good. I'm still going to, at the ground level, I'm going to still put that at 0. It's okay if you put the 0 right where the spout is. It's just for this problem I'm going to do, and you can. It's just going to make it a little slightly different calculation when you come to calculating your force. but I'm going to put my axes right at the top. I'm going to call that X, and if this is 0, good. I do know that if I'm going to draw an arbitrary slice down below, this is my arbitrary slice, that's going to have height delta X. And if I were to go from where it needs to travel down to the slice, that's going to be 2 plus, and this distance is X, right? So distance here that our arbitrary slice has to travel is going to be X plus 2. Good. So that's how you can handle that. So again, we are looking at our units of measurement. We're in US units of measurement, so we don't need to incorporate 9.8 meters per second squared because pounds already has the acceleration due to gravity constant within it. We do want to note that each slice is not going to be the same size. And if it's not going to be the same size, then it's not going to weigh the same amount. And if it doesn't weigh the same amount, it's going to have different force. So the force is also going to be variable, just like the distance is variable here. Each slice has to go a different distance because it's at a different level below the ground. So I want to point out that we do have a triangle here. If we just go from the center of the cone, we would have the shape of a triangle. And we know that this is 4 feet. We know that this is 10 feet. And when we go and draw our R, right, this is going to be the R, where this is my R, right? And why do we want to calculate the R of our disk? Because we're going to want to use the density of water. And looking at the density of water, if I want to look at delta volume of my slice, it's going to be a cylinder again, right? With radius r, it's going to have height delta x, and our delta volume is going to be pi r squared times delta x. It's going to be the area of the base times the thickness, and that's going to give us feet times feet, which is feet squared, and then delta x is in feet, so it's going to give us feet cubed, and we can see that our delta volume here is going to be our pi r squared, or times delta x, and we want to figure out what that r is since it's going to change, and we need to make it in terms of x. And why do we want to find our volume? Because we can get to our force that way. Force is in pounds, and if we just multiply by the volume of our slice, we can get to pounds, right? Because pounds per cubic foot times cubic feet gives us back pounds. All right, so I see that I've got a similar triangles. So in this triangle down here, we know that since I used the distance from 0, the top of that triangle is going to be x. I know that from the top down here is going to be x, and that tells me that this is this distance down here is going to be 10 minus x of the whole thing. I can break the two triangles apart. And I could say that the bigger triangle with 10 and 4 is similar to the little triangle with r and 10 minus x. Good. And what do we know about similar triangles? The corresponding sides are proportional. And that means I can do 4 over 10 is equal to r over 10 minus x. And now I can solve for, or you can do 4 over r is equal to 10 over 10 minus x. You can do the same corresponding sides on one side. It's okay. And solving for r, I end up with 2/5 times 10 minus x is equal to r. So now I've got an expression in x for r. So now coming back to my volume, my delta volume then is going to be pi times 2/5 10 minus x squared delta x. Good. Okay. And so why did I do the delta volume? Because I'm going to move forward with delta force, and my delta force, and remember this is a slice. We're talking about what's the force on that slice, how many pounds does that slice weigh. And our delta force is going to be the density times our delta volume, because we would have pounds per cubic foot times cubic foot, and we're going to get pounds. Good? So what's our density? 62.5. What's our volume? If I do the squares, 2/5 squared is 4 over 25. So this is going to be 4 over 25 pi. And we're going to get 10 minus x squared delta x. And that's going to be our delta force. What's our delta work? Our delta work is going to be our delta force times the distance, and we've already discussed what the distance is to the top of the tank and then plus 2 feet more. Remember, distance down from 0 to your slice is x, but we need to go 2 more, so our distance is x plus 2. And so we're just going to have 62.5 times 4 over 25 pi times 10 minus x squared. Delta x, but I'm going to put the delta x on the other side. But our distance is going to be x plus 2, right? That's our distance. And so now we've got an expression for our delta work. And now we are ready to put together our work function. We might want to expand our polynomials in order before we integrate, and we'd want to go 10 minus x times 10 minus x times x plus 2. The 10 minus x times 10 minus x is 100 minus 20x plus x squared, and then we'll also want to multiply by x plus 2, and multiplying the 62.5 times 4 and then dividing by 25 actually ends up being a nice number, which is 10 pi. And so we'll see that this is going to be 10 pi, and multiplying this out, we're going to get 100, we're going to get 60, and collecting like terms, we're going to get 60x minus 18x squared plus x cubed plus 200 delta x. Good. And that's going to be our delta work. What's our total work? That's going to be the integral of our delta work. And what are the range of our slices? Our slices start from 0 and they go all the way to 10. So we're going to have 0 to 10. Good. And then we're going to end up with 10 pi from 0 to 10 of our 60x minus 18x squared plus x cubed plus 200 dx. And you can integrate that term by term, and you end up with 10 pi. You'll get 30x squared minus 18 divided by 3 is going to be 6. X cubed plus x to the 4th over 4 plus 200x, and we're going to go from 0 to 10. Each one of those terms has an x value, so your f of b minus f of a, your f of 10 minus f of 0 is just going to be f of 10. And so you're going to end up with 10 pi. 10 times 10 is 100, and 100 times 30 is going to be 3,000. So we're going to get 3,000 minus 6,000 plus 10,000 divided by 4 plus 2,000. And whatever that is, we're going to have that be foot pounds. Right? Okay, so hopefully that was useful for you. Sometimes you do need to use similar triangles. Sometimes, if the shape of your slice varies, then you have to take that into account. I hope that you see that pumping fluids involves calculating the volume of your slice, and that's how you make use of the density of the fluid, because your density is usually given in either force per cubic foot or kilograms per cubic foot. So just like the previous example when we dealt with 881 kilograms per meters cubed, we first calculated the mass by using density times the volume. And then once we got our mass, we multiplied by 9.8 to get to our force. And once we get to force, we can approach work, and work being force times distance. And usually with pumping fluids, we definitely have variable distance. And when we have variable distance, we want to use the distance x. So I do think that for regular shapes, it's nice to put the 0 at the top of the tank. Sometimes if you've got circular tanks or spherical tanks, it's much better if you actually put 0 in the center of the sphere, and that might be a bit more complicated. Maybe it's worthy of another video. We'll see. Anyway, I hope you enjoyed, and get to work, pun intended. See you later.